Folate's unseen power lies in its quiet command over epigenetics, the collection of chemical marks, like DNA methylation, that tell our genes when to turn on or off without changing the genetic code itself. These subtle changes don't just affect the individual consuming folate, they can ripple through generations, leaving molecular imprints that shape the health and development of children and even grandchildren. This intergenerational epigenetic inheritance is a remarkable, lesser-discussed dimension of folate's importance. During fetal development, folate is essential to establish proper DNA methylation patterns in rapidly dividing cells. These methylation marks act as the operating manual for the genome, setting instructions for everything from organ formation to the wiring of the brain. When a mother's folate status is optimal before and during pregnancy, it helps ensure that these early epigenetic patterns program healthy growth trajectories and metabolic functions. But if folate is deficient, the fetus may develop altered methylation patterns in key genes, a phenomenon linked to higher risks of birth defects, impaired cognitive development, and increased susceptibility to chronic diseases like obesity or type 2 diabetes later in life. What makes this truly intriguing is that these methylation changes can sometimes persist into adulthood or even be passed on to the next generation, amplifying the consequences of a single period of nutritional inadequacy. Animal studies have shown that folate-deficient diets in pregnant mothers can lead to epigenetic alterations in offspring that affect gene expression related to fat storage, insulin sensitivity, or stress response, and some of these patterns can reappear in the second generation. This highlights how folate is not only a nutrient for today's health, but a steward of tomorrow's well-being. Beyond prenatal health, folate-driven epigenetic changes in adults may also modify disease risk throughout life. For example, certain cancer-protective genes rely on methylation patterns maintained by folate. When folate intake is low, these protective marks may erode, leading to inappropriate gene activation or silencing that can spark tumor development. Meanwhile, in the brain, folate-sensitive epigenetic regulation of genes involved in neuroplasticity could influence susceptibility to mental health conditions like schizophrenia or bipolar disorder, again pointing to a hidden, far-reaching impact of folate on lifelong health. In this way, folate emerges as more than just a vitamin. It is an architect of epigenetic landscapes that guide both our own biological fate and that of generations to come. Recognizing folate's unseen influence on epigenetics invites a deeper respect for this humble nutrient and underscores the profound legacy of our dietary choices, reminding us that what we eat today can literally write the biological script for our descendants' health.